Hello everyone and welcome back to TechOps tutorial. In the previous episode, we deploy our first application using Argo CD and saw how Git defines the desired state. In this episode, we will take that one step further. We will look at how Argo CD can automatically detect the changes and keep the Kubernetes cluster in sync with Git. We will also see what happens when someone makes a manual change directly in the cluster and how Argo CD can restore the expected state automatically. Finally, we will look at rollback option, including Git Revert and Argo CD Rollback. So by the end of this episode, you will understand three main capabilities: automatic synchronization, self-healing, and safe rollback. Before we move into autosync and self-healing, let's quickly recap where we stopped in the previous episode. We created an Argo CD application and used manual synchronization to deploy the application. We also learned the difference between the desired state in Git and the live state in the Kubernetes cluster. Git is our single source of truth for the desired state, and Argo CD compares that desired state with what is actually running in the cluster. We also looked at application status, including sync status and health status. Now there is one important question. Manual sync needs human action. So how do we automate this process? That is exactly what we will cover in this episode. We will look at autosync, self-healing, pruning, drift detection, and rollbacks. Now let's look at why we need automation. Manual synchronization works, but it requires a person to start the sync. That becomes harder to manage as the number of application and deployment grows. The first problem is delayed deployment. Someone has to open Argo CD, select the application, and start the sync. If that person is not available, the deployment waits. The second problem is human error. Someone can select the wrong application, the wrong cluster, or simply miss a step. The third problem is configuration drift. For example, someone can make a manual changes using kubectl. The cluster can then become different from what we have in Git. And the fourth problem is that differences are not automatically corrected when autosync is disabled. Argo CD can detect the difference, but a person still needs to start the sync. What we really need is continuous reconciliation with automatic correction when required. That is where autosync and self-healing comes in. Now let's start with a manual synchronization. Manual sync means that a person or a CI job starts the synchronization when it is needed. We can trigger it from the Argo CD UI using the CLI or through the API call. For example, with the Argo CD CLI, we can run Argo CD app sync followed by my-app. Argo CD then applies the desired state from Git to a Kubernetes cluster. One important point here, after the sync is complete, Argo CD does not stop watching the application. It continues to compare the desired state with the live state. The main difference is that when autosync is disabled, Argo CD does not automatically apply the changes. Manual sync has some advantage. It gives team explicitly control over when changes are applied. It can also be useful when a deployment needs human approval or when teams are still learning Argo CD. But there are also a limitation. Every deployment needs someone or something to start the sync. This becomes harder to manage when you have a multiple application and cluster. So manual sync is useful when you want control over each deployment, but it is not ideal when you want continuous automation deployment. That brings us to autosync. Now let's see how auto synchronization works. With autosync enabled, we no longer need to manually start a sync every time there is a change in Git. The process starts when a developer pushes a new commit to a Git repository. Argo CD detects the new commit. This can happen through pooling or through Git webhook. Next, Argo CD gets the Kubernetes manifest from Git and renders them. It then compares the desired state from Git with the live state in Kubernetes cluster. If there is a difference, autosync is enabled. Argo CD automatically applies the required changes to a cluster. Once the deployment is complete, the application can return to a healthy and sync state. And this process continues. When the next Git change is made, Argo CD repeats the same process. This is the main advantage of auto sync. Instead of someone remembering to start a sync, Argo CD handles the synchronization automatically. This gives us a faster deployment, more consistent releases, less manual work, and clear traceability between Git commits and the cluster state. Now let's look at the main auto sync policy in Argo CD. There are 4 important options we need to understand: automated sync, self-heal, prune, and allow empty. First, automated sync. When this is enabled, Argo CD automatically applies new changes from Git without waiting for someone to start a manual sync. Next is self-heal. If someone changes the live Kubernetes resource manually, Argo CD detects the difference and restores the state defined in Git. Then we have prune. When a resource is removed from Git, Argo CD can also remove that resource from the cluster. This needs to be enabled carefully because it can delete the resources. The fourth option is allow empty. This allows an application to sync even when Git contains no resources. This can potentially remove resources from the cluster, so it is normally kept disabled. For production, the important point is that we should not enable every option blindly. We should enable each feature based on how we want our application to be managed. In the upcoming demo, we will see these settings in action and understand what happens when the cluster or a Git state are different. Now let's understand configuration drift. Configuration drift happens when the live state in the Kubernetes cluster becomes different from the desired state stored in Git. For example, Git says we should have 3 replicas, but someone changes the deployment directly in the cluster and now we have the 5 replicas. The same thing can happen with container image, memory setting, or other Kubernetes resources. There are several common causes of drift. Someone may manually edit or scale resource using kubectl. A hotfix may be applied directly to the cluster using kubectl apply. Helm may also be installed outside the GitOps repository. Even autoscaling can change the replica or resources in the live cluster. Now, why is this a problem? First, different environment can end up with a different configuration. This makes it harder to reproduce an issue. Second, manual changes can be overwritten by the next deployment because those changes were never added to Git. And third, there is an audit gap. A change may happen in the cluster without going through the normal Git review process. This is exactly why Argo CD continuously compares the desired state in Git with the live state in the cluster. Now let's see how Argo CD detects the configuration drift. Argo CD compares 2 things: the desired state in Git and the live state in the Kubernetes cluster. Git contains the configuration we want to run. A Kubernetes cluster contains what is actually running. Argo CD continuously compares these 2 states. If the live state matches what is in Git, the application is shown as synced. But if there is any difference, Argo CD detects the drift and marks the application as out of sync. For example, if someone changes a deployment directly using kubectl, the live state will no longer match the configuration stored in Git. Argo CD detects the difference during its next check. At this point, Argo CD knows that the application is out of sync. What happens next depends on the sync policy we configured. With manual sync, we can review the difference and decide when to synchronize. With automatic sync and self-healing enabled, Argo CD can take action automatically. So the important point here is simple. Argo CD continuously compares Git with the live cluster to detect the configuration drift. Now let's look at one of the most useful feature in Argo CD, that is self-healing. The idea is simple. Git defines the desired state, and Argo CD keeps checking the live cluster against the state. When someone makes a manual change in the cluster, the live state no longer matches the Git. For example, someone could change a Kubernetes resource directly using kubectl. Argo CD detects the difference and marks the application as out of sync. If out of sync and self-healing are enabled, Argo CD continuously synchronizes the application and restore the state defined in Git. Once the sync is complete, the live state matches the Git again and the application becomes synced. There are few important points to remember. Self-healing can correct the changes made directly in the cluster, but it does not fix a wrong configuration stored in Git. Also, self-healing works only when the required sync settings are enabled, and if someone keeps making manual changes, they can keep creating a drift. So the main idea is Git reminds the desired state, and Argo CD automatically brings the cluster back to the state when drift is detected. Now let's look at pruning. Pruning is about removing the resource from the Kubernetes cluster when they are no longer a part of desired state in Git. For example, suppose we have a service called web-v1 in Git and Argo CD has already deployed it. Later we remove the manifest from Git. Without pruning, the resource can remain in the cluster even though it is no longer defined in Git. When pruning is enabled, Argo CD can detect that the resource is no longer part of desired state and remove it from the cluster. This keeps the cluster aligned with Git. But pruning needs to be used carefully because it can delete a real Kubernetes cluster. That is why you should review what will be deleted, control who has the permission to prune, and test the setup before using it in production. You can also use prune last when you want pruning to happen after the other resources have been synchronized. So the key point is, pruning keeps the cluster clean by removing the resources that are no longer part of desired state in Git. Now let's look at a Git rollback. In GitOps, Git is our source of truth. So when we want to restore an earlier application state, one of the safest approach is to change the Git. Here we have three commits. Commit A is our original version. Commit B is introduce a new version. Then commit C introduce another change, but this version is broken. Instead of deleting commit C from Git history, we can use Git Revert. Git Revert creates a new commit that reverses the changes made by commit C. Argo CD then see this a new Git change, compare the desired state with the cluster, and synchronize the previous working state. This approach is especially useful for shared repository because the complete Git history is preserved. You may also hear about Git reset. Reset changes the branch history, so it should be used carefully and generally avoided on shared branches. A good practice is to make rollback changes through a pull request so that changes can be revived and recorded. One important point, rolling back the Kubernetes configuration does not automatically roll back the data that may already have been changed. So for GitOps, the main idea is simple. Use Git Revert to restore the desired configuration while keeping the Git history intact. Now let's look at another way to roll back an application using Argo CD revision history. Argo CD keeps a history of application revision that have been deployed. For example, we have a 3 revision. Revision 1 is version 2.0. Revision 2 is version 2.1.0. Then revision 3, version 2.2.0 is deployed and we find that is broken. Instead of changing it immediately, we can select the earlier working revision and use Argo CD rollback feature. Argo CD then applies the manifest from that selected revision and restore the application to that state. This can be useful during an incident because it is a quick way to restore the application. But there is an important limitation. The broken commit still exists in Git. If automatic synchronization is enabled again, while that the broken version is still in the desired state, Argo CD can deploy it again. That is why an Argo CD rollback should normally be followed by a proper Git revert. So think of an Argo CD rollback as a quick way to restore the application, while Git Revert is the long-term fix that updates the source of truth. Now let's compare Git Rollback and Argo CD Rollback. Both can restore the application to an earlier working state, but they work in different way. With Git Rollback, we change the source of truth. For example, we can use Git Revert to create a new commit that reverses the bad change. Argo CD then detects that Git has changed and synchronizes the cluster. This gives us a clear Git and pull request history. So Git rollback is the preferred approach for a permanent fix. With an Argo CD rollback, we select an earlier application revision from Argo CD and restore the cluster to that revision. This is usually faster because we can restore the application directly from Argo CD without first changing Git. But there is an important limitation: the bad change still exists in Git. If that bad version is still the desired state and automatic sync runs again, Argo CD can deploy it again. So Argo CD rollback is useful as an emergency stopgap, while Git rollback is the better choice for the permanent fix. In simple terms, Argo CD rollback restores the cluster quickly. Git rollback fixes the source of truth. Now that we have covered autosync, self-healing, pruning and rollback, let's look at a 7 practical rule for using autosync safely in production. Rule number 1. Git is the only source of truth. Every production change should go through Git, where it can be reviewed, merged and reconciled with the cluster. Rule number 2. No manual kubectl on production. Direct changes bypass Git and can create a configuration drift. For temporary debugging, use an appropriate ephemeral environment instead. Rule number 3. Enable self-heal carefully. Self-heal is useful for automatically correcting drift, but an intentional manual change can also be reverted automatically. Make sure the behavior is understood and production access is properly controlled. Rule number 4. Use prune with caution. When pruning is enabled, removing a resource from Git can also remove it from the cluster. Combined with autosync, that deletion can happen automatically, so use it carefully and review the required access control. Rule number 5. Always use pull request. Avoid direct push to production branches. Pull requests provide review, approval and an audit trail before changes reach the cluster. Rule number 6. Prefer Git rollback in production. For permanent rollback, revert the change in Git so the source of truth reflects the desired state. Argo CD rollback is useful as an emergency stopgap when you need to restore service quickly. And rule number 7. Monitor sync status. Review application health, sync status and configuration drift before and after enabling these features in production. And finally, one practical tip: roll autosync out environment by environment. Start with development and then staging and finally production. Before we start the live demonstration, let me quickly walk you through the 8 steps we are going to follow. Step 1. Establish our manual sync baseline and confirm the application reaches a healthy state and sync state. Step 2. Enable autosync and self-heal, then make a change in Git and watch Argo CD apply it automatically. Step 3. Introduce configuration drift by manually scaling the deployment with kubectl. Step 4. Watch Argo CD detects the difference and marks the application out of sync. Step 5. See self-heal automatically restore the deployment to a desired state. Step 6. Demonstrated pruning by removing a resource from Git and allowing Argo CD to remove it from the cluster. Step 7. Perform a Git rollback by reverting a bad change and letting Argo CD synchronize the corrected state. And step 8. Perform an Argo CD rollback to an earlier revision as an emergency recovery mechanism. So let's switch to the terminal and get started. At the end of previous episode, we deleted Argo CD application and its Kubernetes resources. So before we start today's demonstration, let's recreate the same application from Git. We won't go through the complete application creation process again. Because we already covered that in episode 4, we will simply recreate the same application and use it as a starting point for this demo. Now I will open Argo CD UI. .192.168.56.115 32645. Click on Advanced, Proceed. Enter the username admin and password. Just like in the previous episode, I will create the application manually through the Argo CD UI. Click on New App. Application name will be TechOps Demo. Project I will choose default. Sync policy I will keep the default manual. And for repository, copy the URL, repository URL, and path. It's episode 4. Destination cluster, choose default. Namespace I will give demo. Click on create. The application settings are the same ones we used in episode 4. The application has been created. Since we are starting with manual sync, I will synchronize it manually. Click on sync. Click on synchronize. Let's go to the terminal. Argo CD app get TechOps demo. TechOps demo. Here you can see the sync policy is manual, but the sync status is sync and health status is healthy. Now let's verify the application resource. Run kubectl get all -n demo. You should see the TechOps demo deployment and service. Then run kubectl get config map -n demo. Here you should see TechOps -demo -html. The application is back in healthy and synchronized state. This is our starting point for episode 5. Now let's begin with manual synchronization. Let's start with manual sync. The repository I have already cloned. So I will pull the latest change. You can run git pull. Already up to date. Check git status. This is the same application directory that we connected to Argo CD. Now I will make a small change to HTML content. So in config map.yaml, I will change version to what I will do. It's already 4. First I will set to 3. Then git add dot git commit -m update application to version 3.0. Let's verify what we have added. It's 3.0. Git push. The change is now pushed to Git. Since auto sync is not enabled, Argo CD will detect the change, but it will not deploy it automatically. I will refresh the application in Argo CD, so it checks the latest state from Git. Go to Argo CD UI. Open this, click on refresh. Here you can see it's out of sync. Argo CD has detected the change and application is out of sync. the desired state in Git is different from the live state in cluster. You can also check the application status from the CLI. I will show you the command. Argo CD app get TechOps demo. Here you can see out of sync. Let's perform a manual sync. I will do it from the CLI itself. Argo CD app sync TechOps demo. This is done. Let's verify it. Argo CD app get TechOps demo. Now you can see the status is in sync and healthy. Go to browser, then refresh the application in browser. It is in sync. The application is back in sync and the new HTML content is now available. Now let's remove the need for manual synchronization. I will enable auto sync so Argo CD can automatically apply changes from Git. Let's switch to terminal. Argo CD app set TechOps demo sync policy automated. Argo CD app set TechOps demo self heal. Enable pruning for our later demonstration. Argo CD app set TechOps demo. Now let's verify. Argo CD app get TechOps demo. Here you can see the sync policy is automated. Now let's open the Argo CD UI. I will show it here. Go to details, scroll down. Here you can see the sync policy. Auto sync, self heal and prune are now enabled. You can also see these settings in Argo CD UI. Now let's test the auto sync by making another change in Git. I will make another change in HTML content. Config map.yaml. I will change this from 3 to 4. Save it. Let's verify it. It's 4.0. Git add. Git status. Git commit -m. Updated application to version 4.0. Git push. The change is now pushed to Git. This time, notice that I am not running Argo CD app sync. You can check Argo CD app get TechOps demo. Wait for the application to return to sync. It is in sync and also it is healthy. Then refresh the application in the browser. Click on refresh. It's out of sync now. It's automatically synced. The new version has been deployed automatically. That's auto sync in action. Argo CD detects the Git change and synchronizes the application without a manual sync command. Now let's look at configuration drift. Our desired state in Git defines 2 replicas. I will now make a change directly to Kubernetes cluster using kubectl without changing anything in Git. This will create a difference between the desired state and the live state. Before we do that, there is one important point. Autosync is enabled, but I am going to temporarily disable self-heal for this part of the demonstration. The reason is simple. If self-heal is enabled, Argo CD will immediately correct the manual change we make to the cluster. That would make it difficult to clearly show the drift and the out of sync state. We will first create and observe the drift, and then we will enable self-heal and watch Argo CD automatically fix it. Let's switch to the terminal. grep-n replicas deployment.yaml. Your Git manifest contains the replica too. Verify the current state. kubectl get deployment TechOps -demo-n demo. The current state is verified. Temporarily disable the self-heal. Argo CD app set TechOps demo -self -heal equals to false. Self-heal is now disabled temporarily. Auto sync is still enabled. This means Argo CD can detect the changes, but it won't automatically restore a manual change made directly to the cluster. Now let's introduce the drift. kubectl scale deployment TechOps demo -n demo replicas equals to 7. kubectl get deployment TechOps -demo -n demo. The deployment is now running with 7 replicas in the cluster, but Git still defines 2 replicas. We have not changed anything in Git. We changed only the live Kubernetes environment. This difference between the desired state and the live state is configuration drift. Now let's see how Argo CD detects this difference. Go to Argo CD UI and click the refresh. Here you can see the sync status is out of sync and we have 7 replicas. After refreshing, Argo CD has detected the difference between Git and the Kubernetes cluster. Git says we should have 2 replicas while the live cluster has 7. Argo CD therefore marks the application as out of sync. Now let's see what happens when self-heal is enabled. Instead of manually synchronizing the application, we will let Argo CD automatically correct the drift. Let's enable the self-heal. Argo CD app set TechOps -demo -self-heal. Enter. Wait for a few seconds, then run kubectl get deployment TechOps -demo -n demo. This is the expected output. Now we have 2 replicas. Then verify Argo CD. Argo CD app get TechOps demo. Sync policy, you can see it is automated. Sync status is synced and health status is healthy. As soon as self-heal was enabled, Argo CD automatically detects that the live state did not match the desired state in Git and corrected the deployment. The deployment is back to 2 replicas and the application is synchronized and healthy. This is the self-healing behavior provided by Argo CD. Next, let's see how pruning works. I will add a small config map to Git and let Argo CD create it automatically. Let's create a new file. Prune-demo.yaml. This is the small code. Save this file. Git add git commit -m. This resource for Prune. demo, git push. The new resource is now in Git. Because auto sync is enabled, Argo CD will automatically synchronize the change. I will refresh the application to trigger an immediate reconciliation. Argo CD UI. Click on refresh. Here you can see Prune-demo. It has been created. Let's verify from CLI. kubectl get conf map Prune-demo. The config map is now presented in Kubernetes cluster and is being managed by Argo CD. Now delete the YAML file from the Git. Git add, git commit, remove prune demo resource. Now I have removed the config map from Git. Because pruning is enabled, Argo CD will recognize that this resource is no longer part of desired state and remove it from the cluster. Let's access Argo CD. I will refresh the application so Argo CD immediately detects the change and perform the pruning. So it has been deleted. Let's verify the pruning. kubectl get config map prune-demo -n demo. Error from server not found. Then check the Argo CD. Argo CD app get TechOps demo. You can verify the sync status is sync and health status is healthy. The config map has been removed from the cluster automatically. This is pruning. When a resource is removed from Git and pruning is enabled, Argo CD removes the corresponding resource from the cluster. Now let's demonstrate a Git rollback. I will first deploy a bad application change. Then I will use Git Revert to restore the previous version. Let's make a bad change. Config map. Here we will change this file.o bad release. Save the file. Let's verify once what we have added. File.o hyphen. It's bad release. Let's confirm. File.o hyphen bad release. Add git commit hyphen m deploy bad application change. Git push. The bad version is now committed to Git. Because autosync is enabled, Argo CD will automatically deploy this change. Go to Argo CD. Refresh it. It's out of sync. Immediately it got synced. Now let's access the application. It shows 4.0. Let's refresh it. Here you can see 5.0 hyphen bad release. Now let's revert the git commit. Git log hyphen one line. I will use hyphen 3. You will see something like this. Deploy bad application change. The important part is that the bad commit is already identified by its commit message. deploy bad application. You can revert it with git revert. Just save it. Now to git push. Instead of changing the Kubernetes cluster manually, I am reverting the bad git commit. This creates a new git commit that reverses the bad change. Now go to Argo CD UI. Refresh it. Then verify on the terminal. Argo CD app get TechOps-demo. Verify it is synced and healthy. Open the application. It's version 5.0 bad release. Now you can see it's 4.0. The previous version has been restored. This is the Git rollback. We changed the source of truth in Git. Argo CD synchronized that desired state to the cluster. Now we will see Argo CD rollback. I will deploy a new version. Go to terminal. Config.map. Here I will do 5.0. Save it. Verify what we have updated. It's 5.0. We can give like emergency release. Save it and run git add git commit -m deploy version 5.0 git push. Now I will demonstrate a rollback directly through Argo CD instead of reverting the git change. Access Argo CD UI. Click on refresh. It's out of sync. It is synced now. Then open the application. Refresh it. Current version is 4.0. Let's refresh now. You can see 5.0 emergency release. Now let's disable the auto sync. Argo CD app set TechOps demo -sync policy none. Now let's verify. Argo CD app get TechOps-demo. Now it has changed to manual. I am temporarily disabling auto sync so that Argo CD does not immediately synchronize the current Git state after a rollback. Now let's find the previous revision. Argo CD app history, TechOps demo. You will see something similar to this. The latest revision is our version 5.0 deployment. You can also verify the Git commits if necessary. Git log one line -5. You will see the deploy version 5.0 and we have also reverted a deploy bad application change. This gives you a clear relationship between what you see in Git and what you see in Argo CD. Use the previous revision ID from Argo CD app history. I am viewing the deployment history in Argo CD. The latest revision ID is 7 in our version 5.0 deployment. This is ID 7. The revision immediately before it, ID 6, is the previous version 4.0 deployment. I will roll back to that revision. You can run Argo CD Rollback TechOps Demo 6. I'm now rolling the application back directly through Argo CD to the previous deployed revision. Let's verify the rollback. Argo CD app get TechOps demo. Then kubectl get pods -n demo. Okay. Now go to the application. The sync policy is manual. I want to show you the application. Here you can see it's 5.0 and Argo CD is out of sync. Now it is showing version 4.0, but still the Argo CD status is out of sync. The application has now been restored to version 4.0 directly through Argo CD. Argo CD app get TechOps demo. Here you can see the sync status is out of sync. Notice that the application is out of sync. That's expected. Git still contained version 5.0, but the live application has been rolled back to version 4.0. So Git and the cluster are now different. Now restore the auto sync. Argo CD app set TechOps demo -- sync policy automated. Argo CD app get TechOps -demo. Now you can see the sync policy is set to automated. Sync status is sync. Earlier it was out of sync. Because Git still contains version 5.0, enabling auto sync causes Argo CD to bring the cluster back to Git defined state. Let's access the application. It is synced. Here the current version is 4.0. Let's refresh. Now you can see it has changed back to 5.0 emergency release. Now let's verify. Argo CD app get TechOps -demo. Sync policy is automated. Sync status is synced. Health status is healthy. Then you can check kubectl get deployment TechOps demo -n demo. It's 2. kubectl get pods -n demo. The application is healthy and synchronized again. The key difference we saw is simple. Git rollback changes the source of truth, while Argo CD rollbacks temporarily change the live application. Now let's switch back to the slide for a quick recap. Before we wrap up, let's quickly review the 6 key takeaways from this episode. First, manual versus autosync. Manual sync requires a human trigger, while autosync applies Git changes automatically during reconciliation. Second, drift detection runs continuously. Argo CD compares the desired state in Git with the live state in Kubernetes and reports difference as out of sync. Third, self-heal means Git wins. When enabled, Argo CD automatically synchronizes the cluster to the desired state when drift occurs. Fourth, Prune deletes with Git. When resources are removed from Git, pruning can remove them from the cluster as well, so use it carefully. Fifth, Git Revert is preferred over Argo CD rollback. Git reverts update the source of truth and provides a proper audit trail, while Argo CD rollback is mainly an emergency stopgap. And finally, production hygiene. Use pull request, avoid manual changes in production, monitor sync status, and enable auto sync gradually across environments. These are the 6 principles to remember when using Argo CD automation in production. That's it for this episode. In the next episode, we will cover managing Helm application with Argo CD. If you found this video helpful, please like, share and subscribe to TechOps tutorials. Thanks for watching and I will see you in the next episode.